to introduce you. Just give me 1 second. All right, can folks hear me okay? Is there an echo? All right, there is no echo. Wonderful. Okay, we can actually get started now. All right.
Yes.
Welcome everyone to another episode of GPU Mode. This is our second lecture in our series on distributed compute. Today, I'm really thrilled to have Professor Didi Munat from Koç University, who's going to give us this wonderful survey she wrote called "The Landscape of GPU-Centric Communication." I first came across this paper when Didi was presenting it to the PyTorch team. What I really liked about it is it really went through the entire history of all the different comms libraries, their trade-offs, what they do. So if you're really looking for a crash course, it's quite comprehensive and historical. I really hope you enjoy this current lecture. So please, without further ado, Didi, take it from here.
Thank you, Mark, for the invitation, and I hope this will be a useful presentation for you all. Okay, so today we'll be talking about GPU-centric communication. By the way, I don't see anything else except my slides, so let me know if you have any questions or you don't see things clearly. Everything.
I'll be monitoring the chat for questions and interrupt you somewhat randomly. So yeah, you can just focus on your slides.
Okay, sounds good. Okay, so before talking about GPU communication, let's motivate first GPUs and then the communication. So, since the early 2000s, we moved to this multi-core era, and then we had to learn multi-threaded, multi-process programming, and we started teaching them at schools as well. And in 2007, first CUDA was released, and it became popular. And actually, my PhD thesis was using CUDA for scientific computing, and that was very rare thing to do at that time. And then in 2010, we started having first GPU-based supercomputers, which ranked first in top 500 systems. And people realize that now they have to learn GPU programming, not just multi-threaded, multi-process programming. We added GPU programming as a challenge. And with today's GPUs are ubiquitous. I'm from HPC world, so I'll give examples from HPC quite a lot. So 9 out of 10 supercomputers, top 500 supercomputers are GPU-based. And so today also, data centers and AI picked up this a bit later than HPC, but the other frameworks, they have the advantage of productivity benefits because they tend to use Python as the programming language. Okay, so basically we cannot escape from GPUs. And another example is this exascale supercomputer, which was kind of a milestone in our field, is a frontier supercomputer. This achieved exascale 10 to the 18 floating points, double precision performance per second in 2022. This is an AMD-based GPU, and it has these 8 GPUs per node, and then there are 10,000 GPUs in the whole supercomputer. So soon you realize that not just programming single GPU is not sufficient. We have to program multiple GPUs and quite a large number of them. Okay, so all of these over the years, when those things are happening, most of us came to conclusion that CPU is no longer is the central processing unit, even though CPU stands for central processing unit. This is similar to GPUs no longer graphic processing unit. So compute has moved completely to other devices, and GPUs gain more autonomy in managing their own computation and communication tasks, and switches can compute, became smarter. And some of the control is still on the CPU side. like you still need CPU for operating system and certain tasks. So CPU has become more of an advanced memory controller. And this is a system balance. I like to refer to as imbalance plot. I borrowed this slide from John McAlpin from Tech. So on the x-axis, you see the years. On the y-axis, you see flops word ratios. So what this plot says is the trend in compute capability improves much faster than improvements in memory bandwidth, network bandwidth, or latencies. So if we had a flat line, which would mean that they increase at the same amount, like if you get a 2x, next year you will get a 2x in latency or bandwidth. But that's not the case. Actually, we have a slope going up. That means the gap is widening between the compute capabilities, how fast you can compute versus how fast you can move the data around. So movement of data is the communication, basically, or the memory accesses, right? So because the gap is widening, the communication optimizations, improvements become more and more important. And if you think of, training costs of, a Megatron model, I'm giving a simple example here. I'm sure you know more recent examples, but this model trained over used 3,000 NVIDIA GPUs, 800 GPUs, and perform 1,000 zettaflop. This is 10 to the 21 flops. And the cost is, if you want to do this in a single GPU, which you wouldn't do, it will take 700 years. And this also costs $6 million, assuming you pay $1 per hour. So this tells you that you not only just GPUs, you also have to run on multiple GPUs. And the cost is pretty high. If you optimize things a bit, you can save quite a bit of money. And time, of course. So I also try to plot the same version of this John McAlpin's system balance or imbalance for NVIDIA GPUs. This is Tensor Core FP16 flop to byte ratios. Again, in the x-axis, we have the year. On the y-axis, I plot flop to byte ratio. So over years, starting from 100 to B200, less than 10 years, Tensor Core going from Volta to Blackwell, there's a 36x improvement in performance. But annealing, even though it doubles its performance, bandwidth every year, it only improved 6x over the years. So this is also an example of widening gap between the compute versus the net or data movement speed. So we related to these, we have an article online. It's called The Persistent Challenge of Data in Post-Exascale Era. If you're interested, you can look at, and it talks about this data movement, data locality issues in recent years. Okay, so this all brings me to this GPU-centric communication. So what is GPU-centric communication? We loosely define it as the reducing the involvement of CPU in the critical path of multi-GPU execution as much as possible, because anywhere that CPU involves, it introduces overhead or synchronization or communication overhead or control overhead. So can we give more autonomy to GPUs, initiating, posting, launching, synchronizing communication? And all of this talk is, actually some of this talk is based on the landscape of GPU-centric communication survey that Mark was referring at the beginning of the talk. So if you want to read, you can find it on archive. We will probably release in a couple of months the updated version of it. Okay, so so this is kind of the timeline of mostly NVIDIA technologies over the years, but AMD kind of follows the same trend. Communication technologies, the timeline and availability, when they become available and what they support. So we color-coded them. There's these green ones, the memory managers, and then blue dots, introduction of GPU direct technologies. And then there's NVLink and mid-switch, and user-level libraries and developer libraries. So in the rest of my talk, I will try to touch some of these, and then hopefully it will be informative and useful for you. Okay, so first, I would like to define some intra-node communication types and inter-node communication types. So in the intra-node communication types, there are 4 types, but we'll come to those. So we differentiate the communication types based on the executor of each operations performed during communication. So for example, here API defines where the communication API call is made by the programmer or by the library. It can be on the host side or device side. By the way, right now I'm just showing the intranode where you have, multiple GPU cards attached to single host, and they are managed by a single or multiple processes or multiple threads, but we are still in the shared memory of, node. Okay, so and then the data path we refer to as who participates in data movement and shows the corresponding the data path. So the green lines here, I don't know if you can see my mouse. Can you see my mouse or no?
I can see your mouse, yes.
Yeah, okay. This shows the data path, and then the API calls, we show this green circles. Okay, let's start with the first type that we will define. We refer to this as host native. Host native is when there's no peer-to-peer access between devices. So there's no P2P communication. So this is the old days how we will program. We will send the data to CPU, and then CPU host will send the data to the other GPU. So both the API is on the CPU side, and then data path is also going through the CPU side. Okay, and the second category that I will talk about is the host control. So with the introduction of GPU Direct 2.0, which introduced GPU peer-to-peer accesses over PCI bus, it enabled direct GPU memory accesses within a node without the host copy. So going from 2 copies, we reduced to 1 copy, and now GPU can read or write directly, make a copy to another GPU directly. So the communication passes directly through PCI, NVLink, or Infinite Fabric interconnects in these cases. And most of the libraries that I will refer later, like GPU, Aware, MPI, Nickel, memcopy operations, they have host side APIs. So they either in category 1 or category 2 perform on one of these. Okay, continuing with device native. In the device native, so we have with the direct peer-to-peer memory access, we can perform the data path just on the device, but also this moves the API to the device as well. So this green circle is now on the GPU side, and very specific examples for the API being on the device side is InVishMem and RuxShMem. They both offer host side and device side API, so they can be either type 2 or type 3. I was just informed that Nickel will introduce also device side APIs pretty soon. It doesn't currently support, but it will in the future. Nickel will be in this category as well. So it will have both device side and host side APIs. And the last type is the host. We refer to as host fallback, which is when the peer-to-peer access is disabled. In this case, communication still takes place. Like you can do direct load store to another GPU remote memory. An API can be within the device on the device side, but in this case, because peer-to-peer is disabled or there's no peer-to-peer communication, then it will fall back to host, and then still communication will take place. It won't issue an error or something. Okay, so these were the intranode communications. Now let's move to internode communications. So internode.
Actually, before you keep going, I just had a quick question, which was so one thing that wasn't too clear to me, it's like for NV shared mem, for example, I've heard some people describe it as, oh, like this is a way of doing comps from like within your kernel, like basically the way you've described it. And then I've heard other people say like, no, it's different. It's like you have this like shared memory model, and all the GPUs can access like the same sort of like global shared memory. And so like how much of Nickel and NVIDIA shared mem are necessarily device versus host coordinated versus just like it happens to be a property of it?
So are you, sorry, I couldn't follow the full question, but you're saying device API versus the host API, is that the question, versus Nickel versus NVSHMEM?
Yeah, so for example, like the question is like, must Nickel be a device or host side API, or must NV shared mem be a device versus the host side API? And if so, why or why not?
Well, okay, they both, right now, Nickel provides the host side API. So you have to make the call on the host side. So that is kind of there's an implication on this, because if you are running the kernel, you cannot issue communication. You need to go back to the CPU to issue that communication call, or you will put in a stream, and then actually that will be the same. So the communication is at the kernel boundaries when you do the API call on the host. So the kernel has to finish to, issue the communication. But in the device side API, you can issue the communications within the kernel, so you don't need to go back to the host. So let's say you produce some data, you will just send it with NVSHMEM. Let's say you do a non-blocking put or get, and then you will resume your kernel operations and then check its completion later on. So there is this distinction between device side and host side APIs. Is that clear?
So that's clear. I think like my confusion was like when you mentioned that like Nickel is considering adding some device side APIs, and I wasn't sure what that
I don't
means
know how
exactly.
it will look, honestly. I actually recently heard this, and I don't know how they will do it, honestly. I don't know. Yeah, so the details are not announced, so yeah.
And then one more question from chat. This is from Vipul Sharma. They're basically asking, where does synchronization happen at those boundaries? Like, is it like implicit, explicit? Does it always happen? So how should we think about this?
Yeah, that depends on the communication library. I'll talk about that a little bit. So if you use NPR or Nickel, you will, because they are using send receive, the communication and computation is kind of together. Like, so communication and synchronization are together, but in NVSHMEM, if you like, the communication and synchronization are separate, because in NVSHMEM, communication is really kind of a memory access. So it's load store. Like in the code, it will appear as load store. So explicitly, as a user, a programmer, you need to introduce the synchronization. So synchronization is more related to the user level library, its semantics, which I will talk about them later in my talk.
All right, we can keep going though.
Okay, so this is more abstract way to presenting. So even we represent GPU NIC and CPUs as small square boxes. So this is more of a like a simplified view, because I'm using these for my teaching as well. So I try to simplify it so that students can get the abstract view of it, and then we talk about details of the libraries and go into the details of them. Okay, so from going into the inter-node communication, going from 1 to 5, you will see that more things move to the GPU side, and there are fewer links or fewer arrows. So that means there's an improvement in the data path. So there are fewer copies, data copies happening. And then another difference is that now we have this purple box, which is NIC, because we are going off node. NIC is involved. And I will introduce two new operations in addition to API and data path. These are register and triggering operations. So we still have the API and data paths. API is on the host or device or both. Either it's supported from the programming language or not. And then the transfer is a stage through host before it reaches the NIC or not. So that's the data path question. And then there is register and trigger. So register is who creates the message and registers to the NIC before sending off node. And trigger is who rings the doorbell to NIC, who signals the NIC to issue the transfer. So these are two operations that we added to the internode. So first is, again, we have host native. Everything is done through the host, all the data paths, and then message construction, registering, and triggering. What I want you to pay attention to, there are three green arrows here. But when we move to the pin host native with the GPU Direct 1.0, it introduced this shared pin memory between GPU and NIC. Before, GPU used to transfer to a kind of a host buffer, and then from that host buffer, another buffer, and then NIC can read from the second buffer. But with this shared pin memory, GPU can put the data in this shared region, and then NIC can read directly from it. So this removed the extra copy on the host. Of course, removing the extra copy reduced the latency between GPU and NIC data transfers. And the third type, which is kind of the milestone, I think, for off-node communication, is GPU RDMA. I think it was introduced in CUDA 5. So this allows the NIC to read and write directly from GPU memory over the PCI. So this GPU memory exposed to the NIC through the bar region. They have to be in the same PCI root complex, but this further reduced the extra copy. If you look at it, we have the two arrows here now. We reduced the one because NIC can directly read from or write into GPU memory. So this eliminated another data path. And this is commonly used mechanism when you do off-node communication in MPI, in NVSHMEM, in Nickel, RICL, all of them for GPU-aware communication. Okay, so the fourth category is now the first three, we improve the data path. And then the fourth category, it improves the control by allowing GPU to trigger the transfers. So CPU will pre-register the messages, and GPU will signal the NIC via doorbell saying that the message is ready, you can transfer. So now this is the GPU Direct Async technology, and it's also known as GPU trigger networking. There's actually a very good paper from AMD published in 2017. It's called GPU trigger networking for intracranial communication. It has very nice figures and explain things, so I highly suggest reading it if you're interested in. So with this GPU triggered networking, there is still this CPU proxy thread that runs on the host. So the last type is the device native. This is truly CPU-free communication, and it eliminates the proxy threads. It moves the the API triggering, message registering, etc. All of them to the GPU side. As you see, that CPU is like gray box here. It's almost like it just had there for the initial kernel launches, but then it's not involved. So this is supported in InfiniBand GPU Direct Async IBGDA in GPUSHMEM. But we realized that this is not configured in most supercomputers to enable this feature. They tend to use 3 or 4. So type 3 or 4, if you have your own system, you should check whether it's configured this way or not, talking to your system admin. Okay, so these are the...
Sorry, just a quick question. You mind going back to your slide?
Yeah.
Again, because I'm not an expert on NICs, so like, my baseline understanding of networking is like, like lookup tables on like a home router. But like the kinds of NICs you're describing here seem fairly sophisticated. Like they can allocate memory, they can like effectively like schedule things. And so like, I'm just wondering, like, could you describe a bit more like what these NICs actually are, like what they like sort of surprising things they might do that might not be familiar to someone who just knows what a single GPU does?
Yeah, so I'm not an expert in NIC as well. So, but either. So, but the NIC, for example, we are referred here from, let's say, NVIDIA Connect X or Bluefield, I think it's called. So those are smart NICs. So they can even do some computation, buffering, staging data, and so it's like mini CPU. They have a compute unit, etc. So. Yeah, I don't know what else to say to your answer to your question.
No worries, yeah, we can keep going there.
Okay. Okay, so this is now I think covered some of the boxes here. Now I will start with some of the purple circles. So these are the NVLink and NVSwitch. You may be familiar with the PCIe, but it's bandwidth is not very high, 50 plus gigabyte per second. But so NVLink provides much higher bandwidth and much lower latency, enables efficient, GPU peer-to-peer communication. And every generation, NVIDIA usually doubles the bandwidth rate, like 900 gigabyte per second in H100 and then 1.8 in B100 Blackwell GPUs. So GPUs can, in order to have fast communication, you need to have all-to-all links. But NVLink, so it's not possible if you have a high number of GPUs, and NVLink is not self-routed, so it requires an intermediate GPU to route the package. So NVIDIA introduced these NVSwitch to do this routing, and now it has all-to-all routing, which makes it very fast connection if you have 72 GPUs, let's say. And AMD has Infinity Fabric Link, which is kind of mimics NVLink. But as far as I know, there's no NVSwitch alternative in the AMD GPUs. Okay, so now we will go into the user level communication libraries. I mean, I'm covering much more stuff than just the libraries. So if you want to know more about Nickel and GPUSHMEM, there was like a week ago, I think Jeff Hammond given a very nice talk in GPU Mode as well. So I highly recommend watching that in addition to watching this talk. Okay, so let's start with GPU-aware MPI because I came from the HPC domain. MPI is the library, parallel programming library that we teach, we use. There are so many legacy code using MPI, and it works. It works when you run 10,000 GPUs or 10,000 cores or million cores, however many cores you want. It scales. It's portable. So that's why considerable effort went into MPI to make it work with GPU. But MPI wasn't designed, it was designed in 1993, so it wasn't designed GPU in mind. So the other solutions came much later, after 2011, 13, I think. So what does GPU-aware MPI means? It refers to MPI implementation that can differentiate host and device buffers. So what does this mean? If you have a send or receive operation, and then it will look at the buffer, and it will say, oh, this is a host buffer or this is a device buffer, so we'll do the transfer accordingly. And it uses GPU direct RDMA and RUGM RDMA. It simplifies code by removing this host staging. Otherwise, you will go to host, and then host will transfer to another host, and then that host will transfer to the GPU. So this basically GPU awareness reduces this extra buffer copies. And API has been always on the host side. So the API calls are issued on the host side. So I'm now showing some of the technologies enable GPU awareness over years. So for example, UVA and IPC, which I will talk soon, they're prerequisite for GPU-aware MPI. And there's the GDR copy and GPU direct. They improve the performance of GPU-aware MPI. And then UCX made it more available, accessible. Okay, so what is unified virtual addressing? So prior to UVA, device to host and device transfer, you need to specify the direction of the copy. But with UVA, you have the unified virtual addressing, which means if you get a physical memory location, you can infer which device it belongs to. So you can do device attribution based on the location or the address values. So it allowed MPI calls with GPU buffers for programming. In early years, they will still stage through the host, but at least the programming was easier because you can just use the device buffers directly. And then there was IPC introduced. IPC is inter-process communication, allow processes to share GPU memory. And basically, GPU will allocate a memory. It will pass the handle to that address to another GPU. And then by using this handle, it will be able to access the memory from located in the other GPU. So this, again, avoided host staging, and it's using GPU-aware libraries. In fact, this is the common way of most common way to communicate within the node at the moment. There is also DGR copy, which is mostly for the small message handling because it doesn't create this handle, but it memory maps to user space, and then it can handle the small messages through the host. And GPU direct RDMA we already talked about, which allows GPU transfers. So I would like to show an example of a tool that we develop in our group, which visualizes the communication and transports used. We refer to as UC trace. It visualizes the CUDA-aware MPI communication. So here, what you see is communication graph. So this is a communication graph of a matrix that used in a sparse solver. This is another communication matrix as a result of running the sparse solver. So you see a lot more traffic here, a lot more links going between nodes. So each node here is GPU, or I think maybe a processor GPU, the same in this case. And then these regions are your nodes. So there are multiple nodes here, I think 16 or no, eight nodes. So when you look at within a node, most of the communication, our tool shows that it's through CUDA IPC. And then if you go off node, it uses this reliable connection, the driver to do the off node communication transports. And then in some cases here, we see that GDR copy is used for small messages. And this graph does a lot of small message communication, and that's why we see higher GDR copy. And actually, our tool can show the top contributing transports as well. So CUDA IPC, for example, 55% of the communication happens through the CUDA IPC, and only 2.5 is the GDR copy. And then off-node communication attributes to 41%, or slightly more than that. And then this is the second input metrics we use, and then the numbers are slightly different because of the this graph does more peer-to-peer communication than this one. Okay, so speaking of UCX, I mentioned UCX in a couple slides back. So UCX is kind of a communication framework, and it's tried to unify the communication protocols. So at the top, you have the communication libraries like MPI, SHMEM, or Nickel. And then it has a communication protocol API, which those library APIs are lowered. And then you go from here, there's a unified communication transport, which kind of abstracts multiple transport technologies like InfiniBand, RDMA, TCP, GPU Direct, IPC, etc. So it will choose the appropriate transport depending on the configuration, message size, whatever hardware is available, etc. So it's kind of the abstraction layer. So our tool UCTrace works with UCX communication framework. Okay, moving to Nickel RICL. These are vendor-provided collectives. I think if you're in AI, you're probably well aware of Nickel RICL. You use them for collective communication. They emerge as a collective communication libraries, but then send receive is pretty important. So they added peer-to-peer primitives as well. It supports the collective operation as like a first-class citizen and fully optimized for annealing, PCI, and vSwitch, InfiniBand, GPU Direct, all of those technologies. And the main difference from MPI is MPI is not stream aware, so it doesn't know these CUDA streams. So what is a stream? Stream is kind of a queue that you put operations, and the operations in a queue or a stream is kind of ordered, so you don't need to add synchronization in between because they will execute in the order they are put in the queue. And this is important for overlapping communication and computation, but or other operations. But MPI doesn't have stream support yet, at least. And RICL is the AMD source counterpart to Nickel. Its API is very, very similar. So if you have a Nickel code, it's kind of very easy to switch to RICL. They're almost the same. I don't know if it's as much as like Control F replace, but I heard it's very similar. So yeah, this is probably everyone knows it, and Nickel is. It also selects the best algorithm depending on the bandwidth, latency of the network, or whatever, whether there's an embedding or not, etc. So it will choose the best let's say, all reduced for your given architecture and configurations. So I put an example code here comparing CUDA-aware MPI and Nickel to kind of have a feeling what's the interface look like. So MPI is send receive based, Nickel as well, there are send receives. So they are both host side APIs at the moment, at least. So the difference is, I mentioned there's streaming. So each operation in Nickel, you also say which stream this operation belongs to. So this means this is put in the stream and then the other one, another one. So that means they will execute in this order. But in MPI, there is no such thing. These are, all asynchronous sends and receives. So before you do that, you have to do CUDA stream synchronize to synchronize operations in a stream. So there's an additional synchronization required for MPI. So there was a question earlier about the synchronization. So this is where we discussed this. Okay, in the GPUSHMEM, or we can say, NVSHMEM, RUCSHMEM, or IntelSHMEM, maybe they call it MonSHMEM. These are, if you're familiar with PIG as partition global address space languages, libraries, this is that. So you have a process as its private region and a shared region, and a shared region is shared with other processing elements, they call it. And it uses one-sided put and get. So put and get, it's remote memory access. It's kind of a load store, but it's a remote, not your local memory, but remote. GPU can access the other GPU's memory through get put methods. And it supports both point-to-point on collective operations. And it has both device-side API and host-side API. It's stream-aware, and these operations, remote operations, can be with different granularity. A warp or thread block can perform those operations. And device-side API is the closest implementation to the CPU-free execution. So it's pretty autonomous execution. And like NVSHMEM particularly gained traction because of the mixture of experts and small LLMs, because you can do efficient local communication within a NVLink domain and access other GPUs memory as its own. It kind of simplifies programming, but it also can introduce errors because you're touching other GPU's memory, you can introduce race conditions. So I'll show an example here. Again, the same code with the Nickel and MPI, but this time I'm showing for NVSHMEM. And this is device-side API. So you have these put signals, and then this is again related to synchronization. This is, yes, you put something, you write into the remote memory, but then the other process can be in the middle of something, like it might be reading and then you're writing, and then it may see half the results, or or you may be reading a stale data you should read after that process writes, etc. So that's why it can introduce race conditions. In order to prevent those, you need to use signal weights, some sort of synchronization in NVSHMEM to make sure the memory ordering, or the state communication ordering, is correct. And another thing is you need to use this collective launch so that you can use the signal weight operations on the device side. Honestly, NVSHMEM codes can be, people say it's easier because you just memory access, but at the same time, it can easily introduce these synchronization or bugs and that be overlooked. One more thing I think we also find, and I think we need such things, is NVSHMEM communication analysis is kind of difficult because they appear as a memory access or you need to, let's say you want to time the communication versus computation. Currently, there's not a good way to do it because, again, the profiling is done outside of at the kernel boundaries, outside of the device. I think there's a question. No?
Yeah, I had a question, and there were questions from chat as well. So what does NBI stand for in the calls on the device?
Non-blocking, I think that NBI, right? You said non. I believe it's non-blocking, but I forgot what I is.
Right, and then okay, the other question I see is from Ayush, which is, like, how would you benefit from like this low-level granularity and control in higher level frameworks like PyTorch? Like maybe this question is getting at what are interesting applications of this.
Do you mean enrichment, this fine-grained control enrichment?
Yes.
Okay. Yeah. So there are many benefits actually if you know how to program it. So enrichment really gives you the very fine-grained communication. Let's say, if you have the data ready, you can ship it. Like you can send it immediately. You don't need to wait this kernel to finish, return to the CPU to send the data as a big chunk. And this is also good for kind of float control. Like when you return back to CPU, it will just send a, let's say, large big message. Here you're sending maybe smaller but more messages, which can kind of benefits in terms of network congestion. Also, you can overlap things here, like you can have one of the block is doing some communication and the other ones are doing the computation. So you're using the other SMs for computation. So you can easily overlap things. In put-get methods, if your application is very unstructured, it has a very unstructured fine-grained communication, that's when people use usually SHMEM type of communication. This is, before NVSHMEM. Like if you have the PGAS models, they were advertised for, unstructured communication. If you have those, they are a good fit. I guess those are the things come to my mind. Yeah. So those are the benefits. But in terms of programming support, like the tools, I think there should be more, like profiling or race detection, or helping developers to debug and analyze NVSHMEM codes. It will be there is a need for it. Okay, I'll go to the next slide, or
Yes, let's keep going.
Yeah. Okay, so at a high level, if we compare these three options, first of all, it's not easy to switch from one library to another. It may require structuring of the code a little bit. Let's say you're using Nickel and then you want to switch to NVSHMEM. You won't do it in a day. It will take some time to do that transition. And so MPI and Nickel is two-sided. There's one-side support, but it's basically send-receive APIs. And then SHMEM is one-sided and asynchronous put-get model. So you need to be careful about these signal operations, and because you're touching other GPU's memory, you need to make sure that you sync with them and not read or write in a stale data, etc. And a stream support, MPI lacks stream support. Maybe there will be in the future, I'm not sure. There were some proposal research ideas how to add it, but I think it's not in the standard yet. But Nickel and NVSHMEM supports GPU streams natively. With Nickel, it has these grouping of communication calls. Maybe I can show. So here you have the group start and group end. You can basically queue these operations in this group. And Nickel will decide when to send those actual transfers by monitoring the the load, the size of the messages, etc. So it has this congestion control a bit inside these grouping calls. Enrichment introduces kind of additional complexity because you're mixing kernel code with communication. So debugging or profiling can be challenging, but those are if you are getting extra performance, those can be overcome. Okay, so I'm sure you're curious about performance differences. Honestly, I refrain from showing some performance numbers in this talk and in similar talks I gave because optimal performance changes depends on multiple factors like your workload, whether you're doing frequent communication or one big communication, your message size or library configurations, library versions, driver versions, and then whether the communication occurs within the node, across node, or you're in an NME-link domain, or there's no NME-link, you have to use PCI, etc. So these are very important factors. So if you do the literature search, I would suggest look at all of these factors before committing one of the libraries. So I say you do not generalize these numbers, so I will talk about some research from our group in a few minutes that we try to unify these libraries as much as we can. We'll see how successful that will be, but we also have these profiling and visualization tools. We think that they are necessary to understand what's going on behind the scenes. I put 2 papers if you're interested in looking at more performance numbers. The second one will be available soon in our group, but if you want an earlier access, I can share it with you after this talk. The first one is published in 2024 by Daniel DeSensi, a colleague of mine. Okay, so some projects in our group. So we because of the complexity of these different communication libraries, we said, can we have a uniform API that will run all of these, and it's stream aware, doesn't introduce much overhead, and we can support both host and device side API, maybe without changing the code that much. So this is our initial attempt, and this paper will appear in IEEE cluster in 2 weeks. My student will be presenting. So the dashed lines are the native library, and then the solid lines are our Unicorn library. If you don't see dash line, that means it's good because it's the performance is the same, so we don't introduce extra overhead. So if you're interested in the code will be released also in 2 weeks when my student presents at this conference in the first week of September. And we also have these 2 visualization tools that are being developed. Some of them we have Snoopy we have a version, you see Trace, it's going to be released soon. So this I mentioned this peer-to-peer accesses and then direct memory loads and stores to remote memory. But if you try to use, for example, Nsight system to visualize these, it will just show you there's some NME-link activity here, but it doesn't tell you who is doing the communication, how much data is sent. And so we decided to visualize these communication graph and communication matrices, and then also attribute objects to these communication calls, like who is involved in communication, which data structures, etc. And we have the source code view as well, which tells, for example, in this line, you do 8% of the data transfer happens here. If you look at it, it's not obvious that this is a communication because you are doing a peer access, and this flag is in another GPU, and you're accessing that's setting a flag in another GPU's memory. So it causes communication data movement. The other, that was Snoopy. The other tool is UC Trace. This is designed for CUDA-aware MPI applications. Here, what we wanted to see is what is transport layer used, in addition to how much data, and then visualizing it, etc. So you can see the NIC, host, and GPU, and then it's clear that this is a node, and off node, you're going here, so there's a link going off node. And the sparse solver that I showed in my previous slide is also generated by UC Trace. This is, for example, two MPI libraries, how they handle their all-reduced ring algorithm. And here, for example, you can see that there's only one node going out and in, accepting incoming and outgoing traffic. But here, two NICs are actually responsible. One is kind of outgoing traffic, one is incoming traffic. So there's a better work balance here in this version and the library configuration. Okay, so this is my last slide. As a summary, I showed why communication is the bottleneck today and will be bottleneck in the future. And then I presented this timeline of in media technology is relevant to communication. And then we try to categorize them as in an abstract way. And then I talk about, the user level communication libraries that you can use to program these, and then a little bit of research projects that we do in our group. And if you're interested, download the paper. There's a lot more discussions there, and watch for the version 2. We will probably have it there in this fall. Okay, thank you very much. I'll stop sharing, or should I? Or maybe this is good. I can now see you as well.
The summary is nice. We can keep it. So
okay,
thank you, Dan. This was wonderful. I guess I had a question, and there was like a few more questions from chat.
Okay.
So I think maybe I'll batch one of my questions with Ayush's, which is like what are sort of like the lower level details of how these tracers that your team developed worked? Was it like you were just using Insight systems, or yes?
No, we are not using Insight systems. We are intercepting the UCX calls and like collecting our own trace. So it's not built on Insight systems. It's completely different. If you are interested, you can send me an email. We will make it open source, but we can give you early access if you're interested in. And also we have paper in draft. I can probably share the paper draft with you as well if you keep it to yourself. Yeah,
that sounds good. And I guess when you publish it, please come back and give a talk on that. So similar to sort of this tracing mechanism, like I think a lot of the interesting work that you guys did was like about sort of showing like there was like this lower level API that was called. Would that give you good guesses as to which like algorithms would be used? Like, for example, if you're like using like nickel and you know that you're on this hardware with this hardware topology with this size, could you predict pretty reliably which algorithms were being like dispatched to? Is this even a secret as far as like nickel goes?
No, you can see actually in nickel you can select the algorithm you want. The tool just verifies, let's say, the selected algorithm and what run is matches, for example. I think with Snoopy we have some nickel tests we run with the ring, and then I forgot the other one. And then you can clearly see that it used the ring versus the other algorithm because we visualize what's going on, and you can verify. And especially UC Trace tool, I think it can be used by different groups of people. Like a programmer can use it to visualize its own communication. Let's say it has two matrices and one is doing terrible and the other one is doing well, and then you can visualize their communication. But also if you're a system admin, you can use it to check whether the transport layers used are what you were expecting, or you didn't configure the system maybe correctly. Or if you're a library developer, you can check eager versus renewal protocol and whether what you expected is what's happening in the transport layer. So these are the things that you can use, sort of verification, maybe performance debugging purposes. You can use them.
All right, sounds good. I think that's it on questions then. Thank you to them. This was wonderful. Please come back when you're ready to publish some of the other tracing work.
Yes, thank you.
And we'll see everyone tomorrow as well. We have we're gonna have the team on Quartet on 4-bit training for LLMs. So thank you so much to them, and see everyone soon.
Thank you. Bye-bye. Thank you.